Alright, this is YouTube Homework 3. Or, excuse me, YouTube Homework 5. So, Newton's second and third laws. Question A. 3 identical bricks are pushed across a table at a constant speed as shown. Hand is pushing horizontally and there is friction. Compare the net forces, magnitude, and direction on system A to that on system B. The essential keyword here was constant speed, so we know that there is zero net force on either system, as they're both moving at a constant speed. So here we are. B, draw a separate free body diagram for system A and B. Label each of the forces. Alrighty, there's my mouse. So we've got weight and normal force being equivalent, of course. Then we've got the force of the hand on object A, which is equal to the kinetic friction and the normal force of system B on system A. Then over in system B, it's a little bit simpler. We're just looking at the force of A on B, the normal force and the weight, which of course are equal, and the horizontal forces are equal, should have mentioned, but friction, the opposite of A on B is the friction of just the kinetic friction on B. Is the magnitude of the force exerted on system A by system B greater than, less than, or equal to the magnitude? Here we know that they are, in fact, equal to one another by Newton's third law, because the force on system B is, of course, A onto B, and the pair to that is B onto A, and they are, just by Newton's third law, equal to one another. Would your answer change if the hand were pushing system B to the left instead of system A to the right? No, they would not. We'd still be looking at the exact same forces, and the magnitudes may be different. However, the forces between each other would be the same, just by Newton's third law. Identify all the Newton's third law action-reaction force pairs in your diagrams by placing one or more small x next to one another. So what criteria did you use to identify the force pairs? And really, it was just that one pair that I had already discussed, because we're just looking at how the blocks are interacting with one another, but we're not looking at the table or within the systems. We're just looking at between the systems A and B. The only forces interacting there are B on A and A on B. Is your answer consistent? Is your answer to part C consistent with your identification of Newton's third law or action-reaction force pairs? And yes, they were. Just because I did in fact use Newton's third law in part C. So there you have it. Moving on. Cut off the question a little bit here, but I will read it. Rank the magnitudes of all the horizontal forces that you identified on your free body diagrams in part B. Alright, so first of all, we know they're moving at a constant speed. Here we have the force of the hand on system A is the largest force. That force is greater than, or it's greater than the kinetic friction on system A. This is kind of tricky to identify. The reason we know that is because the friction of B on A, the force of B on A is equal to the force of A on B, which is equal to the kinetic friction of in system B. And most importantly here, we know that the kinetic friction on A is greater than that of B. And we know that because kinetic friction equals mu times normal force, and we know that the weight of system A is greater than that of system B. So we can infer that kinetic friction on A is greater than these three forces. Did you apply Newton's second law in comparing the magnitudes of the horizontal forces? If so, how? Yes, I did. Here we knew that mass times acceleration equals force of the hand on A minus kinetic friction minus A on B. And then we look at system B, which is just the force of A on B minus kinetic friction. So we know these two are equal, which is going to equal this force by Newton's third law. And then we know that F of K on A is greater than this. So just kind of putting that all together, we have our answer, and we know that this is equivalent to these two forces together. Did you apply Newton's third law in comparing the magnitudes of the horizontal forces? If so, how? The primary thing was just looking at this one third law pair, which really allows us to infer all of the information regarding the friction, because we know that F of A on B equals to the kinetic friction on system B. And then we know the kinetic friction on system A is greater than that of system B, which allows us to rank all of our forces. What information besides Newton's laws did you need to apply in comparing the magnitudes? We know the important thing here is that we need to know that kinetic friction is equal to mu times the normal force. And this allows us to rank our kinetic frictions. Suppose the mass of each brick is 2.5 grams. The coefficient of kinetic friction between the bricks in the table is 0.2 gram, or excuse me, just 0.2. And the bricks are moving at a constant speed of 0.5 meters per second. So this is just kind of an arbitrary fact. The velocity is not very important here. Determine the magnitude of each of the forces that you drew on your free body diagram in part B. So I just go through on either diagram. So let's look at A first. The weight, or mass times gravity, we're using G equals 10 meters per second squared. Weight is 50 newtons. The normal force, therefore, is also 50 newtons. Kinetic friction, we do a little bit of math, so mu 2/10 times 50 is going to be 10. And then the force of B on A, we have to go down here to solve that actually. Not able to get this information directly. So let's go to system B. It's pretty much half for everything. We know that the weight is going to be 25 newtons. The normal force, therefore, will be 25 newtons. Our friction is 5 newtons. And we know that our friction on system B is equal to the force of A pushing onto B and B onto A of 5 newtons. And that gives us the answer to both of these. Would your answers change if the bricks were moving half as fast? No, they would not. Primarily, we just know they're moving at a constant speed, which just tells us there's no net force. We would have the same answer in either scenario. If they weren't moving, we'd be using static friction, and that may make it a little bit different, but essentially the same. All right, next page. Applying Newton's laws to interacting objects. Suppose the bricks were pushed by the hand with the same force as in section 1. However, the coefficient of the kinetic friction between the bricks and the table is less than that in section 1. So we know same force is being applied to the right or in the positive direction. However, there is less kinetic friction, so there should be a net force in either scenario, meaning our bricks will be accelerating. Compare the net force on system A to that on system B. So this is really we'll be using Newton's second law here. F net of A on system A should be greater than that of F net on system B. The reason for that is we know by Newton's second law, mass times acceleration equals our net force, or acceleration equals our net force divided by mass. So as mass increases, our F net will also have to increase proportionally in order for our acceleration to remain constant. So we know that the accelerations are equal between both A and B. And if the mass is double that on A, then our net force has to be double that as well. Draw and label separate free body diagrams for system. Let me check the time real fast. All right, let's go back in there. Okay, so free body diagrams for A and B. They're going to be very similar to our last scenario, but we don't know the friction, so it changes things, and we're accelerating. So here we have weight and normal force, which should be the same. We know that our force of the hand on system A is going to be greater than the opposite forces, which are going to be our normal force, or excuse me, our frictional force, and the force of B onto A. And then over here, we've got the force of B on A, and the normal force, weight, and the kinetic friction. So this is pretty interesting, actually. There is a blurry line here. We can't really decide the order of these forces. Anyway, consider the following discussion between two students. System A and System B are pushed by the same force as before, so they will have the same motion as in section 1. That's just wrong. We know they're being pushed by the same force, however, they don't have as much friction, so there's a net force. Then student 2 says, I disagree. I think that they are speeding up since the friction is less. So now System A is pushing on System B with a greater force than B is pushing on System A. So that was the first sentence, or second sentence I should say, was right. But the force A onto B is the same as B onto A, just by Newton's third law. Alright, so E, rank the magnitudes of all horizontal forces that appear on your free body diagram in part C. Explain your reasoning. So this is kind of tricky. Let's see, so we still know that the force of the hand onto system A is the greatest. We know that F of A onto B equals F of B onto A. But the one thing we don't know is the kinetic friction of A. Because the only thing we can really infer here is that the kinetic friction in system B is going to be less than that of both A and B, or of both the force of B onto A and A onto B. However, the kinetic friction on system A, it could be greater than or equal to, or less than or equal to that of these forces. But we do know that the kinetic friction on A is larger than that of B, just because we know that friction is equal to mu times your normal force. So no, I said it is not possible to rank these forces, and just knowing that there's a net force is what makes that tricky. Part 3. Compare the magnitude. So now we're just looking at the 3 blocks of the system. Compare the magnitude of the net force on system C to the magnitudes of the net force on system A and B. So we'll say that F net of C is greater than F net of A, which is greater than F net of B. You can also say that F net of C on system C is equal to that of F net on B plus F net on system B. F net on system A plus system B. And this is primarily given by the fact that we used this earlier, that acceleration is equal to F net divided by mass. So, of course, the mass of system C would be greater than that of A, which is greater than that of B. However, the acceleration remains constant, so F net has to increase proportionally. Draw and label a free body diagram for system C, and compare forces from A and B. So here, since we're looking at a system, just one system, it's not interacting with anything, we just have 4 forces. That is going to be our gravitational force, our normal force. These two will, of course, be equal. And then our horizontal forces. So the hand onto C, and our frictional force. And, of course, in this scenario, our system is accelerating. Are there any forces on your diagrams for A and B that you did not list? So here, B on A and force of A onto B are not present, and that's because we're just, as I said earlier, we're just looking at a system. And as the book notes, we'll call that, those forces would be considered internal forces here, but right now we are just looking at the external forces. Interpreting free body diagrams. At the right is a free body diagram for a cart. All forces have been drawn to scale. So here, I was asked to draw. So I've got a little table here. We've got a cart and a rope that's pulling off to the right, or it's pulling in the vertical direction, opposite of gravity, and